Let's continue ZAERO training with Section 8, Transient Maneuver Loads Analysis, the MLOADS module. So first we'll go over a little background. The Transient Maneuver Loads Analysis computes the transient loads of the flexible structures due to pilot input commands based on a trimmed flight condition. And we have two approaches available for the maneuver loads analysis for the open and closed loop systems. The first is the state space approach, which requires the rational function approximation, and the second is the frequency domain approach, which does not require the RFA. Now the formulation of the maneuver loads module is very similar to the ASE module, except the aerodynamic control surfaces involved in the ASE analysis are now actuated by the control system, whereas the MLOADS analysis has three types of aerodynamic control surfaces. One, we have the control surfaces actuated by the control system. Secondly, we have control surfaces actuated by the pilot input command. And lastly, the control surfaces that provide a steady state initial trim condition prior to the pilot input. And ZAERO segments your control surfaces that you define by the AESurf Z card into these three different types. But from the user input, when you set up the analysis, for example, you could just have one control surface, one AESurf Z card, an elevator, for example, and it can be used by all three different types. It could be a pilot input command to the elevator. You could have a closed loop control system actuating the elevator, and then also you could have a steady state trim deflection to the elevator. And that's fine. You can do that. So next, the ASE analysis is mainly for stability of the aeroelastic system in the presence of a control system, whereas the MLOADS analysis computes the time domain response of the loads. And next, the aerodynamic forces due to the pilot input commands through the aerodynamic control surfaces can be treated as external forces. And also, since the gust force is a type of external force, the formulation of the MLOADS analysis is very similar to the discrete gust analysis. Now, prior to the MLOADS analysis, an ASE analysis should be performed to ensure that the flight condition is within the flutter boundary of the system. If you try to do a maneuver loads analysis that's outside of the flutter boundary, that is where the system is unstable, then of course your time domain analysis, your states are just going to blow up and go towards infinity. So it won't be a very useful analysis. The plot time bulk data card can be used to output loads in terms of Nastran force and moment bulk data cards at selected time steps so that you can perform some maneuver and then at selected time steps you can export the Nastran force and moment cards and then do a detailed stress analysis in Nastran, a static loads analysis at those specific time steps. So here's the equation of motion of our state space approach. The time domain state space equations of the MLOADS analysis is very similar to the state space discrete gust analysis, except the generalized gust forces are replaced by the generalized aerodynamic forces due to pilot input command, as shown by this equation. So our left-hand side should be familiar, it's the same, and then on the right-hand side we have the aerodynamic forces. We have the QHH times the normal modes, QHC times delta, and this would be the delta due to the closed loop controller. And then next we have the pilot input command. So this QHP is identical to QHC, except the subscript here just denotes that this QHP or QHC is multiplied by the external pilot input command. And then our P naught here is the generalized forces at the trim condition. So our bullet points here, QHP is the generalized aerodynamic forces due to control surface deflections. That's commanded by the pilot inputs, delta P. And then MHP is very similar to MHC. That's our inertia term up here that I originally skipped, except that's for the control surfaces commanded by the pilot input. So this delta double dot is our closed loop controller. So this gives us the inertia term, and then this delta $P is the pilot command. And of course, since the system is linear, you can just think of it as MHC times delta plus delta P. So next, moving on to the P0 vector here. The vector P0 represents the generalized forces at a trim condition, which can be expressed as G plus Q infinity times Q times the delta trim. So G is the generalized forces due to gravity at a given load factor. This Q0 here is the generalized aerodynamic force matrix of those trim variables that provide the steady state initial trim condition prior to the pilot input. And then delta trim is the trim variable vector, which can be obtained by a trim analysis. So for example, if you do a trim analysis and you find that your angle of attack is, say, 1 degree, and then your elevator is 2 degrees, then this delta trim would include that elevator deflection of 2 degrees. Now, in order to ensure a perfect trimmed condition prior to the pilot input command, the initial condition of C0 must be obtained by the trim analysis. So once again, if we do that trim analysis and we find that the angle of attack is 1 degree, our elevator is 2 degrees, in addition to that, ZAERO will give you the static deformation of the aircraft, which would be in C0. So that entire trim solution would be your initial condition in the maneuver loads analysis. So next we'll review the RFA. So if we apply the rational function approximation to the generalized aerodynamic forces, that gives us this equation. So now we've got both QHC and a QHP. So our A is made up of AHH, AHC, and AHP. And remember, AHP is the same as AHC. It's just only those control surfaces that are due to pilot input. AHC is only those control surfaces due to the closed loop controller. And then similarly, E is made up of EH, EC, and EP. Now the RFA of QHH, QHC, and QHP leads to the state space aeroelastic equations for the open loop response analysis given in this equation, where our XAE is made up of C, C dot, and XA. And XA are the lag states. XA, the lag states, are given here by this equation. Now the AAE and BAE are the same as those as the ASE analysis. UAE is the control surface vector commanded by the control system. And then UAP is our pilot input and trim. So this delta P is the control surface deflection commanded by the pilot input. And then the 1 is here for our trim input. And then BAP is given by this matrix. And you can see the last column here is for our trim condition. So that has the P0 in it. So this quantity multiplied by the 1 will give us the trim command. So next we'll move to the plant model and closed loop system. So combining the state space equations of the actuator model and the aeroelastic system yields the state space equation of the plant model given here. And notice that our pilot and trim are still external forces here and here. So now combining the state space equations of the plant model and the control system, and then closing the loop by the gain matrix, leads to the closed loop state space equation. X dot V is A bar V times XV plus B bar VP times UAP. So you can see our stability is exactly the same as the ASE analysis because our A matrix is the same. The pilot input and the trim is an external forcing function. Now the state vector XV consists of C dot, and XASE, where this XASE is made up of our lag states, our actuator states, and our control system states. Next week, we'll look at how we can replace the rigid body aerodynamics by user-supplied values by the MinIMP1 bulk data card. Now, after the transformation from the principal axis to the body axis, the rigid body submatrix and the generalized mass matrix is no longer diagonal. In fact, it's the same as the rigid body mass matrix of the flight dynamic model. So our MHH is made up of MRR, representing the mass matrix of the rigid body states, and MEE, representing the mass matrix of the elastic states. And the MRR in the body axis is given here. So we have the mass of the aircraft, and then we have the inertia terms here. Now the submatrices and the rational function approximation matrices associated with the rigid body modes contain the aerodynamic stability and damping derivatives that can be replaced by wind tunnel data or CFD data. So our AHH naught RR, so the RR is the 6x6 rigid body portion of AHH naught, and then our AHH1 RR is given by this matrix. Now in these two matrices, the theta naught and phi naught are the Euler pitch and roll angles, and G, which is seen here, here, these two spots are the acceleration due to gravity. Now the inclusion of these two gravity terms plays a key role in predicting the phugoid mode. So this you set in the min-IMP or the min-IMP1 bulk data card. Now if you do not include the min-IMP or the min-IMP1 bulk data card, ZAERO of course will calculate all of these terms for you and use the ZAERO calculated terms. But if you have the wind tunnel data or CFD data available, you can specify these coefficients and ZAERO will replace the terms in these matrices with the data that you provide. Next we'll look at the state space equations specified in the airframe states by the MLDSTAT bulk data card. Now for a symmetric flight condition, there are generally 6 airframe states denoted as X, H, theta, U, alpha, and Q, where X is the perturbed forward position, H is the perturbed altitude, theta is the perturbed Euler pitch angle, U is the perturbed forward velocity, alpha is the perturbed angle of attack, and Q is the perturbed pitch rate. Now the transformation matrix that relates XAS to XR is given here. So on the right, these states are the airframe states, and on the left we have the normal body states, TX, TZ, TX dot, and TZ dot, and then RY and RY dot. So this is for the 6x6 symmetric condition. So for example, if we look at TZ dot, we can see that TZ dot equals minus V, where this V is the velocity, minus V times alpha plus V times theta. If we look at TX, TX is just minus X. Now for the antisymmetric flight condition, XAS contains the antisymmetric airframe states, Y, beta, P, R, phi, and psi. So Y is the perturbed lateral position, beta is the perturbed side slip angle, P is the perturbed roll rate, R is the perturbed yaw rate, phi is the perturbed Euler roll angle, and psi is the perturbed Euler azimuth angle. And the transformation matrix that goes from the airframe states to the rigid body states is given here. So after the transformation, our new state space equation is given here. So ARR and BRR, the terms here and here, are identical to those of the flight dynamic model. And then you can see we have the cross-coupling terms here, and then this is the purely elastic portion of A. Now we'll look at the frequency domain approach in ZAERO. So the frequency domain equations of motion for the MLOADS analysis is very similar to the frequency domain discrete gust analysis, except the generalized gust forces are replaced by the generalized aerodynamic forces due to the pilot input commands, as shown by this equation. So the first two terms here on the right-hand side are the same as we've seen before, but now our new external forcing function is our delta P, so that is the pilot input. So this BAP of I omega is given here, where our QHP is of course the aerodynamics on the control surfaces of those control surfaces that the pilot is actuating. Now the closed loop frequency domain approach for the maneuver loads analysis is then derived as follows here. So once again, you can see that our stability is unaffected by the pilot input. The pilot input is just the external forcing command. Now the dynamic maneuver loads recovery procedure from the time history solution of the state vector is very similar to that of the discrete gust loads analysis. In general, we have two approaches, the mode displacement method and the summation of forces method. The equation for applying the mode displacement method is identical to that of the discrete gust analysis, and the aerodynamic loads involved in the summation of forces method is expressed here. So our aerodynamic forces is our dynamic pressure times our spline matrix times SKJ. Remember, that's our integration matrix among the boxes. And then we take the inverse Fourier transform of our forces in the frequency domain on the boxes to convert to the time domain. So we have our AJH times C, AJC times delta, and then AJP times the Fourier transform of the time domain pilot command. So next we'll look at the bulk data cards, or the new bulk data cards. So we have the MLOADS card, which is basically the same as the GLOADS card that we saw previously in the discrete gust, but this is for maneuver loads. We have our MLD command for the pilot input command, and then we've already seen the MLDTRIM, MLDPrint cards. The MLDTRIM defines the steady state initial trim condition, and then the table D1, which we've seen a few times, defines a tabular function for use in generating the frequency dependent or time dependent table. Now, to compute the inertial loads, it's required to import the MGG matrix through the assign matrix executive control command, and the MGG matrix can be exported from MSC Nastran using this DMAP alter. So you can see here's our output for command to export the MGG. And we actually have two examples here. The second one has additional precision, so this is full double precision output to the ASCII file. Next, this is the bulk data card interrelationship for the transient maneuver loads analysis. As I said, the MLOADS card is kind of the main driver bulk data card. So in our case control section, we have MLOADS equals an ID number. This refers to the MLOADS bulk data card with that identification number K, referred to by the case control section. And then for the state space approach, we call out to the MLDSTAT card. We always refer to a Flutter card to define the Aeroelastic system. For a closed loop system, we refer to the ASE controller. And then we have the MLDSTAT card to define the airframe states. The MLD command defines the pilot input command. And then the MLDTIM defines the starting time, ending time, and time step. And then MLDPrint is used to output parameters of interest. So the MLDTRIM card specifies the initial trim condition that's computed by the trim module, and then MLD command card specifies the pilot input command by a table input via the table D1 bulk data card. This is the MLOADS bulk data card. So we have the ID number. The Cont ID field refers to the ASE controller card. The Flut ID field refers to the Flutter bulk data card. The RAA ID field refers to the MLDSTAT card. Now, if RAA ID is blank or 0, then the frequency domain approach is used. And when RAA ID is positive, then that integer refers to the MLDSTAT card for the state space approach. The states field refers to the MLDSTAT card, which allows you to specify the airframe states. The command field refers to the MLD command card, specifying the pilot input. The time field refers to the MLDTIM card, specifying parameters of time integration. And then lastly, the MLDPrint field refers to the MLDPrint card, which allows you to output a time history of parameters of interest. Now the MLOADS card is referred to from the case control section. Now notes here, the structural finite element model must contain rigid body modes. So the support field in the assign FEM command must be specified. Now remember, when you use the assign FEM and you just do a Flutter analysis, if you have rigid body modes, you don't have to include the support card. It's not actually required. However, we do recommend it. But for the MLOADS analysis, the only way for ZAERO to know that the rigid body modes actually are rigid body modes is to use the support option. So that tells ZAERO that you have rigid body modes, and then it tells you which rigid body modes you have. Next, unlike the trim discipline, where only half of the model is required for an asymmetric flight condition, the transient maneuver loads analysis requires both sides, so a full span model, to be modeled if you want to do an asymmetric maneuver. And then if you want to output component loads or forces at grid points, then the matrix KGH, SKGH for symmetric or asymmetric, or AKGH for antisymmetric must be imported. And the way to get the KGH matrix, you can either import it directly or you can import the MGG or MGH matrix. In that case, as we've seen before, ZAERO will calculate MGH for you based on the input MGG, and then it will calculate the KGH based on the MGH. And then in the fix mock, fix MATM, or fix MDEN cards, only the first flight condition is used, as noted here. Also, the fix HATM is not allowed. And the analysis is done in the analysis units, and the analysis units, FTM unit and FTL unit, are specified in the fix card. This is the MLD command card, which allows you to define the time history of the pilot input commands. So we have an ID number, which is referred to by the MLOADS card, and then we have an open-ended input where you can specify as many pilot input commands as you would like. So we have an EXT-INP field, which refers to an external input bulk data card. So this is the control surface where the pilot command is applied. And then the ID tab field refers to the table T1 bulk data card, which specifies the time history of the pilot input command. And then as a note here for closed loop systems, as I said earlier, you could have an elevator which is actuated by both the closed loop control system and the pilot input command. In that case, you need a C-junct card which will add together the signals from the pilot command and the closed loop system. So you could have a simple C-junct with a 2-input single output C-junct card where the first input is the closed loop controller, and then the second input is from the external input bulk data card. And then that C-junct will add together those two signals, and then that will command the elevator. Next, we have the MLDTRIM card, which allows you to specify the initial trim condition. So we have an ID number. Next is the gravity field. This is the acceleration due to gravity, where the units are an FTL unit per second squared, where FTL unit is the length unit defined in the fix card. So those are the analysis units, not the model units. Next, we have NZ, which is the initial load factor. Next is thick cam. This is a character string, either yes or no, and we would recommend thick cam always to be yes. The reason is that this is the influence of the mean flow condition from the trim flut card and the camber effects in the PA foil 7 bulk data cards. So if you have an airfoil defined on your wing and you want the mean flow condition to include the camber effects from that airfoil, then you would want thick cam to be equal to yes, which is what you would want the vast majority of the time. However, you can specify thick cam equals no, which will exclude those effects. So basically, unless you really know what you're doing, don't set that to no. Always set thick cam equal to yes. Next, we have the modal field. This is a character string which matches a matrix name. That matrix can be specified by the DMI, bulk data card, or the assigned matrix. This contains the modal coordinate solution of the structure modes at the steady state trim condition. This modal coordinate solution can be obtained from the output file of a trim analysis. And if modal is blank, all of the modal coordinates at the trim condition are assumed to be 0. So when you do a trim analysis in ZAERO, in the output file, it will print out a DMI bulk data card for you that you can simply copy and paste into your MLOADS input analysis. And so that DMI entry contains the static aeroelastic deformation of the aircraft at the trim condition. Next, we have a open-ended input where you can specify the trim conditions of the control surfaces. So trim var is a character string that matches one of the program-assigned trim variables, such as alpha, which would be angle of attack, or the control surface type of trim variables, for example, elevator, described in the trim var bulk data card. And then value is the value of that particular trim var. The units are defined in the trim var bulk data card. So once again, in the trim analysis of ZAERO, when you look in the output, you can see what the value of all of your trim variables are. So for example, your alpha could be 1 degree and your elevator could be 2 degrees. So when you look at the output of your trim, then you'll copy those values into the MLDTRIM input card. So at time 0, you'll start out at a trimmed condition. So to note here, this remark 2 refers to the gravity and NZ fields. The normal acceleration is gravity times NZ times cosine of theta naught, where theta naught's the initial Euler pitch angle theta that's defined in the MLDSTAT card. And the normal acceleration is active only for symmetric and asymmetric maneuvers. This is an example in remark 3 of the DMI card. So this would be in your ZAERO output file from the trim analysis, which you would copy and paste into your input. For this particular example, we can see that this is from a symmetric analysis. We have 3 rigid body modes. So the modal coordinates of the 3 rigid body modes are all 0. And then for our elastic coordinates, we have these non-zero values. And the program-assigned trim variables include alpha, beta, p-rate, q-rate, r-rate, and thick cam. So the total resulting force and moment induced by the initial load factor, gravity times nz times cosine of theta naught, the mean flow condition, which is thin cam, the modal coordinate solution of the structural modes, and all of the trim var with the value. So the total resulting force from these contributions should be 0 in order to satisfy the steady state trim condition at the initial time of the transient analysis. And of course, that is what the trim module of ZAERO does you. It tells you what the values of all of these different contributions should be such that your total forces are 0. So we'll move on to an example here of the MLOADS analysis. So this is for a forward swept wing with a flutter suppression controller. The forward swept wing has 3 control surfaces and 3 rate sensors for flutter suppression, and the pilot input command is specified to TE flap 2. So this is our trailing edge flap 2. And the example here is going to compute the time histories of the wingtip acceleration, wing root bending moment, and stresses in the C-bar element. So we have our TE flap 1 control surface, TE flap 2, and our canard. These are the 3 control surfaces. This is our canard, this is our wing, and then this is our vertical tail. So we'll look at the definitions of the 3 control surfaces. The AE-surf-Z canard is the canard. These are the aerodynamic box IDs. This is the ID number of the actuator bulk data card, and this is the actuator transfer function. And then we have our TE flap 1 and TE flap 2. So these are the 3 AE-surf-Z bulk data cards, and these are the 3 actuators. So for example, if we look at the TE flap 2, that refers to the actuator with ID 1006. this is our actuator definition. So we can see that this value is this value here, and then our 77,000 is right here, and then our 274 is right here. Next we have our three sensors, and I've included both versions of our sensor. We have ASE sensor, which is our old style sensor input, and then we have our ASE sensor 1, which is our new style input. So and you wouldn't put both of these in the input, you would just choose one or the other. So I believe in our test case, we actually have this version because it's a very old test case. But if you were writing the test case today, we of course would use this card because it's easier to decipher. So if we look at the first sensor here, it's a rate sensor, structural grid point 121. So if we look at this, we can see grid VT3. From the V, we can see that it's a rate sensor. The T3 means that it's in the Z direction of the output coordinate system, and then it's at grid point 121 with an ASE sensor ID number of 101. So you can see that's very simple to read. When we go to the old style definition, we can see that it's grid point 121, and then the component number is 3, but we have to remember that this 1 here means that it's a grid sensor, and then also that it's a grid rate sensor. So you have to look that up in the user's manual to decode what these numbers mean as to what the type of sensor is. So this is a little bit harder to understand, which is why we recommend the ASE sensor 1 style of sensor. Next, we'll look at the LQG Flutter suppression controller that we have. So the LQG controller has 38 states with 3 inputs from the 3 sensors and 3 outputs to the 3 actuators. So this controller is kind of complicated. We're measuring all 3 sensors, and then we're actuating all 3 of our control surfaces. So we have our CONCT card, which connects the sensor to the MLOADS card, which defines the LQG controller, and then we have the CONCT cards, which connect the output of the controller to the actuators. Now the ABCD matrices of the LQG controller are stored in a file called abcd.dat, and they're imported into the program by the assign matrix command. So we can see the matrix name that we're storing this matrix on the ZAERO runtime database is ABCD. So now our MLOADS bulk data card, which defines the LQG controller, refers to this matrix name ABCD. So you can see here we have 38 states, 3 inputs and 3 outputs. So this matrix is going to be size 41 by 41. This LQG controller can increase the flutter speed from 1300 feet per second to 1500 feet per second at Mach 0.9. And this density. So this, if we do an open loop analysis, this is our resulting VG curve for the critical mode, and then in the closed loop analysis, this is the resulting VG curve for the critical mode. So you can see we've pushed the flutter boundary from about 1300 feet per second up to 1520 feet per second. So we do the stability analysis first to see where we can do our maneuver loads analysis. So we'll do that next. So next we'll look at the pilot input command. The pilot input command to the control surface TE flap 2 is specified by an MLD command bulk data card, which refers to the external input and table D1 bulk data cards. So this is our MLD command. The external input is here, and then our table is defined here. So we have 0 from time -2 up to 0.1, and then we ramp up from time 0.1 to time 0.16 up to a value of 0.05, and then we hold that until a time of 0.66. Then we ramp down from a time of 0.66 to 0.78 to -0.05. We hold that until a time of 1.28, and then we ramp back to 0 from time equals 1.28 seconds to 1.34 seconds. And then we hold that 0 signal out to 100 seconds. So next we have a C-junct card, which has 2 inputs and 1 output. The first input is the control command from the MIMO controller for the third control surface, TE flap 2. And then the second input is the pilot input command defined by the external input card. So as I just said a few slides back, we have the C-junct card which adds together the signals from the closed loop control system and the pilot command. So the inputs of the C-junct are the control system and pilot command, and then the output of the C-junct is fed to the actuator. Next we have our ASE controller card. So this refers to the surf set, and the surf set card lists out our 3 control surfaces. It refers to our senset card, which lists out our 3 sensors. It refers to the TF set card, which lists out the MIMO SS and the C-junct. And then it refers to the CNCT set card, which lists out all of our fixed connections. And then these are the remaining fixed connections we have, which connect the 3 sensors to the MIMO SS, and then the remaining 2 outputs of the MIMO SS to the remaining 2 actuators. Next, we'll look at the rigid body modes of the forward swept wing configuration. So the structure modal solution is imported by the assign FEM command. So we have our support option here equal to -135. So from this we can see that we have 3 symmetric rigid body modes, and the minus sign indicates that we want ZAERO to clean up those rigid body modes. And so we do recommend, in addition to specifying your rigid body modes, including the negative sign. Now the fore-aft rigid body mode is removed from the 3 symmetric rigid body modes by the MList entry in the Flutter card. We're not interested in including this mode in our analysis, so we just want to exclude this mode from the analysis, and that's done through this set1 card referred to by the Flutter card. Next, for the state space approach, the RFA is applied to construct the state space equation by the MLDSTAT card with ID 140. So this MLDSTAT card refers to our aero lag. This aero lag card defines 4 aero lags, and we're explicitly specifying the values of these lags. Normally, you don't need to do that. I think this is just kind of for illustrative purposes, showing that you can specify the 4 lags directly if you want to. And then the AP const card here is our constraints. And this shows our recommended constraints, where we have DA0 set to 1, and then no constraints on DA1 and DA2. Lastly, we have the rigid body reduction card to clean up the rigid body modes. So the RB red card specifies grid point 90. So this is the point where the rigid body modes, the reference point for the rigid body modes. So we're cleaning up modes 3 and 5 because mode 1, remember, we're excluding from the analysis. As another option, instead of specifying the grid point 90 in the RB red card, you could specify it in the support field by specifying -135/90. So personally, I would recommend putting the 90 up here in the support because then you don't have to worry about including it in the rigid body reduction card. Next, we're going to convert the rigid body modes to airframe states. So the 2 rigid body modes, which are the pitch and plunge modes, are transformed into the 4 airframe states, alpha, Q, theta, and H, by the MLDSTAT card with ID 100 that refers to the MLDTRIM card to define the trim condition. So our MLDSTAT card here defines our 4 airframe states, alpha, Q, theta, and H. Meanwhile, the MLDSTAT refers to the MLDTRIM card with ID 100. Now the trim solution for the 1G cruise condition is first solved by performing a trim analysis with 2 trim variables, alpha and canard. The trim solution and the modal coordinates of the deformed structure under the trim loads are specified by the MLDTRIM card with ID 100 here. So our gravity term is 32.2. We have an NZ of 1. Thick cam, as I said, always set that to yes. And then our modal solution is supplied to us from the trim analysis. So we've copied and pasted that into our input. And then additionally, our canard and alpha was solved from the trim analysis. So we've copied those values here into the input. So the trim loads are the initial loading condition for the MLOADS analysis. These trim loads satisfy the trim condition. Therefore, before the pilot input command starts, all the responses should be constant and equal to the trim solution. If you don't do that, then a transient response occurs right at time 0, because the time domain solution will try to find the trim condition. Next, we want to define what kinds of outputs we want to look at. So we have 6 parameters which will be printed out through the MLD print card. We have the time derivative of alpha, the airframe state alpha. We have the modal displacement of the first elastic mode, the modal acceleration of the first elastic mode, acceleration of the structure grid point 90 along the z direction, and stress at c bar 110, and then finally the wing bending moment at the wing root. So this is our MLD print card here specifying those outputs. The wing root bending moment is defined by a load mod card given here. Now we're going to use 3 methods to compute the wing root bending moment. The mode displacement method, the summation of forces method using the inverse Fourier transform, and the summation of forces method using the RFA to compute the aerodynamic forces. So the first MLD print card uses the mode displacement method, and then our remaining parameters of interest, because they do not involve forces, don't depend on the solution type. So our 2 remaining MLD print cards only need to specify the load mod card. So the summation of forces with inverse Fourier transform is this MLD print card where we have SOF equals yes, and then the summation of forces with RFA is this MLD print card where the SOF entry is equal to RFA. And also note that the 3 MLD print cards all have the same ID number, so they're all referred to from our MLOADS card, and so all 3 of them will be active. This is the interrelationship for our analysis. So our MLOADS card, as I said, refers to where our MLD print, here they are, MLD print, our 3 MLD print cards. We have 3 plot time cards to have an animation output, and then we have our closed loop control system defined here. So we have our MIMO-SS, which is our LQG controller, and then this is our C-junct, which is adding together the external input. So we have our external input. That's one of the inputs to the C-junct. The MIMO-SS is the second input to the C-junct, and then the output of this C-junct is fed to the actuator. Whereas our other 2 control surfaces are directly connected to the controller, the MIMO-SS here. These are the results. So the acceleration and stresses are calculated directly from the time history of the generalized modal solution. Therefore, they're independent of the loads recovery method. So our acceleration at grid 90 is here. We've actually started the simulation at time -2 seconds. So you can see the response is flat from -2 up until the about 0.166 seconds. That's when our pilot input command starts. So this is the acceleration response. This is the stress SA1 and stress SB1 at C bar 110. And these are modal stresses defined by the DMI entry. Next, we'll look at the 3 different solution methods for the component load. So this is the wing root bending moment. Our mode displacement is the solid black line. The RFA is the dashed dotted line, and then the SOF, summation of forces, is the dashed line. And the SOF method usually gives the most accurate results. And you can see that all three methods agree decently, but the SOF method, once again, like we said, is the most accurate. Next, we'll compare the transient response of the closed loop computation through the frequency domain approach and the state space approach. So the frequency domain approach is activated by specifying RAAID equal to 0. So if we look at the acceleration at grid 90, you can see that we have a very good agreement. So that indicates that we have a good RFA. And then this is our stress SA1 and SB1. Once again, we've got a very good agreement. So we'll move on to the wing root bending moment. So on the left, we have the mode displacement method. On the right, we have the summation of forces method. Now the good agreement of the wing root bending moment computed by the state space approach and by the frequency domain approach verifies that the RFA involved in the state space approach is accurate. So just as a reminder, if you do some sort of controller design external from ZAERO, of course you're going to be relying on the RFA, and then also, you'll be relying on the RFA. So you'll use that to design the controller. So then when you do the analysis in ZAERO, you want to go ahead and use the state space analysis to verify that you get the same answer as you expect, but then you also want to do the frequency domain analysis because that is the more exact method, and then that will also once again verify that you have a good RFA.